The next speaker today, Nikolay Abrosimov from Sobolev Institute of Mathematics. He will speak about explicit volume formula for a hyperbolic tetrahedron in terms of edge lengths. Please.
Thank you. First of all, I want to thank the organizers for such a nice conference and for the opportunity to give a talk here. I will talk about our joint result with Bao Wong, who is also here. His talk is the next one. The calculation of volume of some polyhedron in three-dimensional space of constant curvature is a very old and difficult problem. Probably the first known result in this direction belongs to Tartaglia, who described the algorithm how to calculate the height of Euclidean tetrahedron with some concrete edge length. The formula which expresses the volume of an Euclidean tetrahedron in terms of its edge length was given by Euler, and the multidimensional analog of this result uses the Cayley-Menger determinant. More precisely, let T be an Euclidean tetrahedron which, with the edge length dij. So dij denotes the edge between vertices I and j. Then the volume is given by this quadratic equation whose coefficients are integer polynomials in terms of dij. The problem of calculating volumes remains relevant. This is partly due to the fact that the volume of a fundamental polyhedron is main geometrical invariant for a hyperbolic three-manifold. And since Mostov-Prasad rigidity theorem, it is a topological invariant also. Every three-manifold can be represented by some fundamental polyhedron. That means we can pairwise identify the faces of this polyhedron to construct a three-manifold. Thus, the volume of manifold is the volume of its fundamental polyhedron. It can be considered as the volume of its fundamental polyhedron. So consider a hyperbolic space, or Lobachevsky space if you want. A compact hyperbolic tetrahedron is a convex hull in this metric of 4 points in the hyperbolic space. Let's denote the vertices of T by numbers, 1, 2, 3, and 4. Then we denote the edge lengths by Lij. So Lij is the length of the, so is the distance between vertices I and j. Also, we put theta ij for the corresponding diagonal angle. A Gram matrix of a tetrahedron is defined as follows. It consists of minus cosines of diagonal angles. Consider an edge matrix. An edge matrix of a hyperbolic tetrahedron consists of hyperbolic cosines of edge lengths of a tetrahedron. And it is known fact that a hyperbolic tetrahedron is uniquely up to isometry defined either by the set of its diagonal angles or by the set of its edge lengths. So any of them, a Gram matrix or an edge matrix, contains all the information about the hyperbolic tetrahedron. This is unlikely to Euclidean case, where only an edge matrix defines the tetrahedron up to isometry. But a Gram matrix defines Euclidean tetrahedron only up to simility. But there is no notion simility in hyperbolic space. Well, it is a very difficult problem. I mean, in most general formulation, it's a difficult problem to find the exact volume for hyperbolic polyhedron of prescribed combinatorial type. In this general formulation, it was done only for hyperbolic tetrahedron, which is the most simple polyhedron, I mean, in sense of combinatorial type. Even for general hyperbolic octahedron, it is an open problem. Nevertheless, if we assume that a polyhedron admits some non-trivial symmetry, then the volume calculation is essentially simplified. We can say that, firstly, this effect was shown by Lobachevsky. He found the volume of an ideal tetrahedron, that is a hyperbolic tetrahedron with all vertices at infinity. So consider an ideal hyperbolic tetrahedron. Since all vertices are at the infinity, then the sum of diagonal angles adjacent to each vertex is equal to pi. And consequently, we have that the diagonal angles along the opposite edges are equal to each other, so it has a symmetry. The following formula was given by Milner, so he found a very simple and elegant formula for the volume of ideal tetrahedron, which was originally computed by Lobachevsky. It is just a sum of 3 Lobachevsky functions, and the arguments here are diagonal angles, A, B, and C. And the Lobachevsky function is defined here. Well, we can say that the family of all ideal tetrahedra can be parameterized by 2 independent parameters, for example, angles A and B. A more complicated case with only one vertex at the infinity was investigated by Ernest Borisovich Winberg. Also, Lobachevsky found the volume of biorthogonal hyperbolic tetrahedron, or so-called hyperbolic orthoscheme. And the next theorem presents the formula given by Coxeter for this case. So we consider a hyperbolic tetrahedron with 3 so-called essential diagonal angles A, B, and C, and the remaining diagonal angles are supposed to be pi over 2. Then its volume is expressed by this formula. Here S is a so-called Schläfli function defined below. Despite that above mentioned very important but still partial results, a volume formula for arbitrary hyperbolic tetrahedron has been unknown till very recently. The general algorithm for obtaining such a formula was indicated by Xiang in 1988, and the complete solution of the problem was given by Cho and Kim in 1999. But the formula given by Cho and Kim was not symmetric in the sense of rearranging the arguments. Then Jun Murakami and Yana found a symmetric formula, and Akira Ushijima find a geometric proof for Murakami-Yana formula, and also described the case of truncated hyperbolic tetrahedron. In these papers, the volume of a tetrahedron is expressed as a function involving 16 de-logarithm or Lobachevsky functions, whose arguments depends on diagonal angles of a tetrahedron and some additional complex parameter, which is a root of some quadratic equation with complex coefficients. And geometrical meaning of the obtained formula was recognized by Libon from the point of view of Frege symmetry. And an excellent exposition of these ideas and the complete geometric proof was done by Yana Mahanti in her PhD thesis. Here is Murakami-Yana's formula. This is a definition of de-logarithm. L is an auxiliary function in terms of complex variable zeta. It is related with Lobachevsky function. This is an imaginary part of L. And here is a formula. And well, you can see that indeed it involves 16 logarithm functions. And the arguments are diagonal angles, A, B, C, D, E, and F capitals, and additional complex parameters Z1 and Z2, which I didn't describe on this slide because it takes too long. In 2005, Derevnin and Mednych suggested another formula for the volume of a hyperbolic tetrahedron. So, well, consider a hyperbolic tetrahedron given by its diagonal angles. Well, we define some auxiliary parameters. V1, V2, V3, and V4 are just the sum of diagonal angles adjacent to corresponding vertex. H1, H2, and H3 are the sum of diagonal angles along the Hamiltonian cycle of edges. Hamiltonian cycles. Then the volume is given by this integral. Logarithm of product, etc. And the limits of the integral Z1 and Z2, well, different Z1 and Z2 than in the previous formulation, sorry for that, are appropriate roots of the integrand expression. And more precisely, Z1 and Z2 described here on this slide. But I will not stop on that. Surprisingly, but more than 100 years ago, Italian mathematician Sforza already found a formula for the volume of arbitrary hyperbolic tetrahedron. This formula is shown on this slide. So the main trick by Sforza is that we assume that all the diagonal angles are fixed except one, for example, theta 3,4, which is a formal variable. And then the volume is given by this integral. And here C34 denotes the 3,4 cofactor of the Gram matrix. And we assume that the functions inside the integral C34 and determinant of G are the functions in one variable theta 3,4. And we denote it by T just to distinguish the variable of integration and the limit of integration. A new and simple proof of this formula was given in our paper with Alexander Mednych. And what we use to produce the proof? Well, of course, we use a Schläfli formula, and we use the main trick by Sforza. And also, yes, we need the following properties of the Gram matrix. So this theorem collects results from these two papers by Ushijima and by Mednych and Pashkevich, published in the same year. And the main part is this one. This is the formula or cosine rule, if you want, which express the lengths in terms of Gram matrix, in terms of Gram matrix cofactors. And also, well, okay. Let me briefly remind again the results, the main results related with volume calculations for hyperbolic tetrahedron. So Lobachevsky found the volume of hyperbolic orthoscheme, and more than 100 years later Coxeter found a simpler version of this result. Also Lobachevsky found the volume of an ideal tetrahedron, and Milner found a very elegant version of this result. Then Weinberg computed the volume of a hyperbolic tetrahedron with at least one vertex at infinity. Well, and the last sentence, the last paragraph here represents 4 different formulas for the general case, for arbitrary hyperbolic tetrahedron. But all these formulas are expressing its volume in terms of diagonal angles. Well, there is one more paper by Jun Murakami and Akira Ushijima, 2005, where they suggest an approach how to calculate the volume of a hyperbolic tetrahedron in terms of edge lengths. But there is no an explicit formula in this work. One can just use partial derivatives of not explicit functions involving 16 d logarithms to compute the volume in some given concrete edge lengths. And the natural question arises, can we find some explicit formula for the volume of a hyperbolic tetrahedron in terms of edge lengths? And we tried to do that. So consider again the age matrix of a hyperbolic tetrahedron. First of all, we need an existence theorem, existence criterion for a hyperbolic tetrahedron, not in terms of diagonal angles, but in terms of edge lengths. And here it is. There are 3, two-sided inequalities, right? And I can explain what they mean. So for the first inequality, it is just a triangle inequality for 3 sides. Well, first we take a distance L12 to be just any positive real number, right? Arbitrary positive real number, L12. Then the first inequality is just a triangle inequality for the triangle with sides 1, 2, 1, 3, and 2, 3. Then the second inequality is a necessary and sufficient condition for the existence of the triangle in hyperbolic space with side lengths L12, L24, and L14. Okay. And if we set the distance between vertices 3 and 4, then we get a rigid construction. And the last distance named L34 cannot be chosen arbitrarily as we want. We have some limitations. So the shortest possible distance between these two vertices, 3 and 4, is attained when the diagonal angle along the edge 1, 2 is equal to 0. And our flexible construction became flat. The longest possible distance between vertices 3 and 4 is attained when the diagonal angle along the edge 1, 2 is equal to pi. And again, our construction became flat. And we can compute these minimal and maximal distances. We call them L1 and L2. And we get this existence theorem, existence criterion in terms of edge lengths. But I tell the idea of proof of this theorem not only because it is simple. More important that now we have the explicit construction in hyperbolic space. We have the family of hyperbolic tetrahedra with rigid faces, 1, 2, 4 and 1, 3, 4. Oh, sorry, 1, 2, 3 and 1, 2, 4 with common edge 1, 2 and variable distance between vertices 3 and 4. And we have a sharp two-sided bound for this variable distance. So this construction is explicit, and even in the case of classical, Sforza formula, we have no such an explicit construction when 5 diagonal angles are fixed and just one diagonal angle is variable. But here we have. Then we prove the analogous properties of the edge matrix of a hyperbolic tetrahedron, as we saw before for the Gram matrix, right? And the most important part is this expression for the cosine of diagonal angle in terms of cofactors of the edge matrix now. And here, taking indices 5 minus I and 5 minus j is nothing more than the reflection of the edge matrix with respect to second diagonal and nothing more. So we can write it in this way or in this way. I should note that this most important part can be also found in the paper by Akira Ushijima. The necessary instrument for us is Schläfli differential equation, which relates the volume differential, edge lengths, and differentials of diagonal angles. And also we use so-called Jacobi equation, which relates different cofactors of a quadratic matrix. And using these results, we find this formula. Well, let T be a compact hyperbolic tetrahedron given by its edge matrix. we denote Cij the cofactors of the edge matrix. And now we assume that all the edge lengths are fixed except one, for example, L34, which is variable. Then the volume of a tetrahedron is given by this integral. And we consider the cofactors as the functions of one variable L34, denoted by T, just to distinguish the variable of integration and the limit of integration here. Well, you can say that, one can say that this formula is more complicated than the classical Sforza formula, and I agree, I completely agree. But the reason is the following. Well, consider once again the Schläfli formula for a hyperbolic tetrahedron. Well, I can write here minus is due to hyperbolic geometry, 2 is due to dimension, and on the right side we will have six guys. And when we use the approach by Sforza, we fix 5 diagonal angles. So 5 guys here are just zeros. And what we get is just, well, you see. But in our approach, we have that, well, I can show you again this construction. When we change the distance between vertices 3 and 4, when the L34 varies, all 6 diagonal angles also arise. So what we have in Schläfli formula? Well, the derivative of volume by L34, our variable of integration, we have, well, as a derivative of the composite function, we have a sum by all the edges. Sum is over all 6 edges. And of course, this guy can be substituted by Schläfli equation, and we get this sum. So here we have the sum of 6 guys. Previously, we had just 1 guy here. We should integrate. So we can expect that the analog of Sforza's formula, but in terms of edge matrix, should be at least, roughly speaking, 6 times more complicated than the original one. But we will succeed to simplify it using Jacobi equation for many, many times. Not just once, as we did for the classical Sforza's formula. Okay, still this formula is very complicated, and a good idea is to double check it somehow. So we put every edge length to be equal some positive real number A, and as a corollary we get this more simple formula for the volume of a regular hyperbolic tetrahedron, compact regular hyperbolic tetrahedron with all the edges equal to some positive real number R. And this formula is numerically coincide with the following previously known formula. So this formula for the volume of a regular hyperbolic tetrahedron was given by different authors in different works. For example, one can find it in the book of Hedges Toth, or in this work by Yakut, Salas, and Kader. And I can explain why we couldn't expect that the previous formula from the corollary and this formula, we couldn't expect that they will be the same. Because, well, probably, well, in our case, what we have? We have, well, we have this tetrahedron. I draw it again. Hyperbolic tetrahedron, right? And how we integrate this this distance between vertices 3 and 4 is a variable of integration. So we take the flat picture, volume is 0, the diagonal angle along the edge between vertices 1 and 2 is equal to 0, and we have this flat construction. And here is the minimal possible distance between vertices 3 and 4 in our flexible construction, right? We denote it by L1 previously in the existence theorem. In the case when all the edges are equal to each other, of course we have here just a regular triangle, with sides equal to A, right? And here all the edges, all the white edges are equal to A. And the distance between vertices 3 and 4 is 0. So we integrate by, well, this is L34, or we denote it by T. We integrate from 0 to L34 by T, from 0 to A. T is a variable of integration. But the differential form, the integrand, is different because in this case, the latter theorem, we integrate all the edges at the same time. So we started from a point where t is equal to 0, right? And then our tetrahedron grows and grows, all the edges at the same time. So that is why the integrand is different. But still we can compare the results numerically. So at this, actually I can stop on this point because the application of this formula for the volume of a hyperbolic tetrahedron in terms of edge length, one of the possible applications is to get a formula for the volume of antipodal hyperbolic octahedron, for example. And I hope this application will be considered in the next talk by Bao, right? So I can stop here. Thank you for your attention.
Okay, let us thank the speaker. Questions from Zoom, please.
Maybe I have a question. Do you think there's an isometric formula?
There are many formulas, and some of them are very nice for the volume of a hyperbolic tetrahedron. I think that the classical Sforza's formula is very nice, but it expresses the volume in terms of edge lengths, in terms of diagonal angles. But sometimes we need the formula in terms of edge lengths.
Okay.
Do you think there's an isometric formula in terms of edge length?
Isometrics.
Probably, but we didn't find it yet.
Of course, you could just average this formula and get one.
Sorry?
You could just average this formula over all permutations of the label and get a metric.
No, now I understand. Certainly, this formula is symmetric because we this formula is symmetric. We can rearrange the vertices 1, 2, 3, and 4 in any way. We can permute them, and nothing will change here. It is symmetric, actually.
One more questions? Okay.
Have you any restriction to dimension of hyperbolic space?
Well, this formula is just for 3 dimension. Three-dimensional hyperbolic
What
tetrahedron.
about high dimension? What about high dimension? No one. Nothing.
We don't know. We don't know nothing. But of course, there should be some adequate formulas for the volume of n-dimensional hyperbolic simplices, not necessarily regular ones.
Yes.
More questions? Remarks? Okay. Let us thank the speaker again.